Welcome back, and today I would like to check our code and we will fix something if we find any potential issues, and then we just switch to the next step. I wanted to prepare the linear layer. Let's check transpose for a moment, yeah? We have this backward method for the transpose, and we provide the gradient for this transpose and axis. But I think that it won't work fine if we provide an axis, because in case if we have an axis of the transposition, we randomly swap the axis in our matrix, and we need to have the backward action for such transformation. And I think that this transposition with the gradient, if it works only if axis is none. In this case, we can return just numpy transpose the gradient, and we just reverse the transpose, and it works fine and pretty straightforward. But in case if we have an axis, we need to reverse or just inverse permutation of the axis, and else just second case, yeah, we need to compute the inverse permutation of the axis. So let's create a variable inverse axis, and we can utilize the tuple, and let's use the numpy arc sort. This numpy arc sort finds the inverse order to revert the transpose, yeah? And then we need to transpose the gradient back with this inversed axis. And I think that right now we cover two scenarios. When the axis is none, we just transpose the gradient back. In case if we have an axis, we find the inverse order to just revert this permutation and return back the gradient with this inverted axis that restores the original order of the gradient matrix. I realized that I missed one method in our module. Let's call it Params count. Let's mark the return type by integer, and then we just create number parameters. Then let's create a sum of, we know that we can run the self.parameters. This action just returns a bunch of parameters for our module, and we can sum them up, yeah, using the loop. Let's create the loop for parameter or param in self parameter. We need to call param.size, and we know that parameter, it keeps the tensor, yeah, it's just the children of the tensor class, and inside the tensor class we have this size that basically just provide an access to the data size, and we can just return this sum. We sum up the size of every parameter of our module and return. It can help us to understand how much parameters, yeah, what the size of this, what dimensionality of the parameters we have for this current module. Just for the test, let's create the class dummy module. And we provide module as the parent of this class. And I want to create a constructor. We define one argument. Let's call it just dimensions as the integer data type, and we can save this dimensions to the self.dimensions. And we need to create one parameter, param, as the parameter, and we provide this dimensions to the parameter. And we can overload the forward, and here we have an x variable as the tensor. And we need to return something. Let's return x.transpose. Yeah, nothing more. Okay, now let's initialize this code. Okay, and for the test, let's create a model. We use our sequential and compose together a bunch of dummy modules. Let's say that we use 10 dimensions for the dummy module number 1, 100 dimensions for the dummy module number 2, and 1k dimensions for the dummy module number 3. And let's call the params count for this module. Let's rerun this code. Okay, we have a problem, and yeah, I think that this is the pure typo, yeah, if data is not in none. Okay, let's find this line. It's right over here for the parameter. We need to check if data is none, of course. Yeah, that's clear typo. Let's run this again. Okay, and for this issue, we have this descriptor init of super object needs an argument, yeah? It's for the sequential, and I think that we have no any useful action in the parent constructor. We can just drop this string. Let's run it again. Okay, and it works, yeah? And we definitely sum this dimensions up. One little thing that I want to add to the parameter, we have this alpha for the leaky. It's the slope of our leaky function, and we just predefine this parameter, and we have no any option to change this alpha. Let's add this alpha term right over here and put it to the init. Yeah, we have gain and alpha. Yeah, and this is basically our init, gain, alpha, and init. It's the last piece that I want to fix at this moment. Okay, we are ready to move on for the next steps. Linear layer is the next big thing that I want to develop. Linear layer rely on matrix.product instead of vector operations or any other type of implementations like loop or whatever, because the matrix.product allows efficient computation on the backend side. In our case, it's NumPy library, and NumPy processing multiple input samples simultaneously, and we have highly efficient implementation of this operation in the NumPy or any other library. At layer I, the transformation is defined as you can see on the screen. We can define it as the operation a subscript I from x, and we multiply, we just make a dot product between the input x and the weights matrix W subscript I, plus the bias term at this layer B subscript I. And we can make such step, yeah, for a single layer like this. We just need to apply the sigmoid function for the result of this computation, yeah, of this dot product of matrix X with the weights W plus the bias B. And the deep neural network just applies these transformations layer by layer, and we apply the sigmoid for every layer. We have some type of composition, yeah, and we have the notation of functional composition in the mathematics, yeah, and we can write it like this. It's very convenient way to represent such step-by-step computations, yeah. We just move data by the pipe, yeah, from right to left side of this equation. Okay, and for the implementation, let's define class linear layer, or let's call it just linear. We have module as the parent of this class, and then let's move to the constructor init. Every layer has its own dimensionality, and we have the in features. Let's mark it as the integer data type, out features integer, and we use this in and out features when we create the parameters. Let's just save this in features to the self, and same for the out features. Okay, and we need to define the weights matrix. Of course, we use the parameter class. Let's create self.weights and call the parameter, and we provide the out features and in features. And also we have the init method inside the parameter. Let's add this parameter init method and utilize the init method data type. By default, let's use the Xavier initialization and provide this init method. And one more parameter, bias, as the boolean, and by default let's install it to true. Okay, and we need to init the bias term again as the parameter. We utilize only out features and init method. Let's use the same init method as for the layer, probably. If bias, else none. But this is probably not the best strategy to initialize bias. Just duplicate this init method. Let's use, instead of the init method, let's use the normal distribution and define the gain. For example, let's use gain 0.01. Yeah, we define the bias as a very tiny random value, very tiny, very small random initialization, and it can help to break the symmetry during training. Yeah. Okay, and I think that we are ready to move on to the next step of the implementation. Let's implement the forward method. And first steps of our implementation, we need to check the dimensions of input tensors. If the number dimensions not 3 or 2, we just raise the value error, because we work only with 2D or 3D tensor. Yeah, it's very important for our implementation, because we always have the 3 dimensions, for example, and first dimension, it's the batch dimension, how many batches do we have, yeah, and the next 2, it's just the working data. But in case if we have more than 3, it's something wrong. Yeah, there is something wrong, definitely. And we need to check that the last dimension of input matches with the input features. And if we have no match with the input features, we raise an error that the last dimension of the input does not match input features. And as the next step, we need to compute this dot product. Yeah. And sorry, I realized that we multiplied the input times the weights matrix transposed. Yeah, it's an important point. And here we need to implement something like this. Let's create an output variable, and then we multiply x times the self.weights.transpose. But there is an important point. We have no this operation. We have no the dot product between matrix and matrix inside our Tensor class. And it's something crucial for this implementation. Yeah. And before we just finish this implementation, we need to implement the dot product for the Tensor.